discover our new number, which you guys already know. And so what we're going to do is we're going to go through the formula we already know. This formula is for compound interest. And what we're going to do is we're going to look at it in incrementally smaller periods of time. So the first one is, if I gave you $1 and 100% interest, how much would you have after a year? It's probably a good idea. Okay? So, you see that one is already 2. Worked out for you. So now let's go back and see how that would change if we incrementally made those time periods smaller and smaller and smaller and smaller. All right, so the first one is semi-annually.
You can do this one. Oh no.
It still hadn't come on?
Yes. Man.
All right.
Right ideas made really.
All right, so semi-annually is going to change the denominator to a 2.
Yep.
And throw a 2 in here. And so let's see how that changes. For semi-annually, we get 2.25. Okay, our next one is quarterly, so how's that going to change? Quarterly changes the 2's to 4's. Whoever's humming, I need you to stop. Who's humming?
Slowly talking.
Where's the next door?
All right, the next one is monthly. So monthly, the 4 would change to a 12. All right, now let's take a look and see how it's changing. It started off at 2, then it went 2.25, and then 2.411, and then 2.6130. Okay, give yourself about 6 decimal places.
Oh.
Right, and you can just write the answer. I got the work. You write the answer.
Thank you.
Okay. After monthly comes daily. So what do we change the 12 to?
365.
365.
Hey.
Oops. All right, so let's see what that gives us. All right. Oh, we're getting closer. 2.714567. That's fun. All right. So that's daily. The next one would be hourly. Guys, how many hours are there in a day?
24.
24. So if I just take that right there and put times 24 times 24, that should do it, right?
Whoa.
That was days times hours. So now I get 2.718126669.
Couldn't you just write 24 without 365?
Nope, that would be 24 times a year.
Oh, okay.
That would be bi-monthly. All right, the next one, by the second. So we got to figure out how many seconds there are in an hour. So there's 60 seconds in a minute and 60 minutes in an hour. So that's 3,600
Wow.
seconds. So I'm going to throw in a times 3,600. Hey, they're starting to look very similar, aren't they?
I don't want to prove.
Wait a
I don't get it.
I'm mad.
Why do you have to multiply by 24?
We all are.
That's 80.
That's how many hours are in
Well, it's just so big, it's not enough to write it down.
But wait a minute.
I'm going to go steal these and post it. I don't think it's going to work, but the last one was by the second, right?
By the second, yep.
By the second. All right.
7182817.
All right. So We'll go back to our little Desmos. We can steal the previous one.
By the quarter second.
All right, so that was just hourly. Slide that in. Woo. Slide that in there. All right, now I got to do by the half second and by the quarter second. This is getting a little ridiculous,
It really is.
but we can do it. All right. Now see if I can steal all of these at once.
Oh, I think this too.
60.
That's pretty good. All right, so let's go do the last two by the half second and by the quarter second. So if it's half a second, I'm just going to do it on this last one. That's just multiplying by 2 times 2 times 2.
Stop looking up.
Okay? And that's what we get.
They defer a little bit.
All right, we'll shrink it up so it can fit in here a little better.
I don't.
All right, these are starting to look very, very similar, aren't they?
Yeah.
Okay, and now let's go do quarter of a second. So if this was a half, if I change this to a 4, it would be a quarter of a second. All right, so what do you notice about these last two?
These are really similar.
Oops.
I noticed that I can't make it move. There we go.
Oh wait.
They're identical, aren't they? Do you think they're identical if we looked at the decimal 100 places down the road?
No.
No, they wouldn't be identical. But what we have basically created is a very nice approximation for our new number.
E.
Our new number E. Yeah, this is when math gets weird.
Math has always been hard.
Okay, that's fair. In middle school, you learned about that other weird number, pi.
Pi.
Sadly.
Yeah, so
Seventh
maybe
grade.
5th, 6th grade, yeah.
I want to say
Sixth or
around a
seventh
6.
grade.
Yeah, 6.
Okay,
You're
7th,
very
I don't know.
short.
So you learned about pi. So what's the decimal approximation for pi?
3.14.
3.14. And you're okay with that. That's right. 15926. Very good. Okay, so this is a nice decimal approximation for our new number. And our new weird math number is a letter. It is E. All right? I don't know where A, B, C, and D went, but it is E. Okay? There's a reason why it's E. But
Why is
it has to do with the language.
So
And not
E-
it's not the one we use either.
So E is 2.71 or E is
2.71828.
2.7182.
Yeah. Okay, so what this gives us is a really nice approximation for E. Now, E is approximately 2.71828.
Can we write this where it says what?
Sure, write it where the notes go. I'll scroll mine down there so I can find the notes too. I don't need that. Okay, so E is approximately, we should really have squigglies here, 2.71828
Why squigglies?
Because it's approximate.
because it's approximate. You know how pi is really weird and it's irrational? Irrational tells me I can't write it as a ratio. It's never ends, it never repeats. It's a decimal that goes on forever. E's its good buddy. They're the same. Okay? So that's why we say it's approximate. And the way we built this, we were doing compounding. If we got to where we were compounding every single moment, it's one of these things that's hard to wrap your head around. Like, you know, when you try to think about what infinity really is, or if you try to think about the Earth's actual position in the universe and what lies outside of that, and after a while your brain just hurts
It does.
because it's not truly capable of understanding that. There's some math topics that are like that just make my brain hurt because I really want to have a good global understanding, but I was just given this tiny little brain that doesn't do it.
I just want to
So this is one of those things. If we were to compound continuously, every moment, I wouldn't even say every second because we just got down to a quarter of a second.
Every nanosecond.
Even more than that, which we can't really understand. What we have created is a situation that compounds continuously. And when we do, that base, that multiplier becomes E. And so our formula looks like this. It's very simplified. It's much easier than the other formula. It's principal E, our new number, to the RT. Now, let's have a little discussion about E and our calculator. This is, it is PERT.
Part.
Yeah. It used to be, when I first started teaching, there was a shampoo. It was called PERT. It was green. It had an interesting scent. But I don't think PERT exists anymore. But E is our new number. Now this is different than E. Okay? Lowercase e represents our new weird number.
Still weird.
Uppercase E on our calculator represents what?
Exponential.
Scientific notation. Yes, it does.
What?
Oh, okay. With the calculator. All right. So these are not the same thing. So when you're using E on the calculator, and we're talking E, our new buddy, our new number, use the lowercase e, not uppercase. Different meaning. Very different. Okay? Now, E is our natural base. And if any of you are into science,
Yes.
anybody in here enjoy science? Okay.
Okay.
If you look at a lot of equations that are used in science, E shows up all the time.
Yeah.
E can be used to model lots of naturally occurring events, which is what science studies.
I just remember
Okay.
my mole.
So, you will see E in lots of your equations. Now, when E is raised to a power, we have to take the log. And E is so special, just like base 10 is special. E is so special, it has its own log. It's the natural base. So when we take the log of E, it's called the natural log. Now with a natural log, the base is always E. Now this is where some of you will be excited and others have already not shown excitement. The great thing about this is all the properties that work for natural logs are those same properties we already learned for regular logs. So we've done log base 10, the common log. We've done log base 2, base 5, base 3, base 8. Now we're just doing log base E. So instead of writing log base E, we have a shortcut for that. It's called natural log. Now, the reason we say the words natural log and then we write it ln,
Logarithm natural.
that's right, it's a logarithm natural. And he is absolutely correct. We didn't name it.
Who named it?
No, that is a good question, and I used to know the answer. I will answer that tomorrow. Okay? That's terrible. But in many other languages, the adjective comes after, and that's why it's ln. All right? Now, we're going to talk about how we're going to use this, and this is going to be simple.
E.
You always say that, but it ends up not being.
No, this is simple.
That's what you said about logarithms.
Just looks weird.
It does look weird. That is correct. Looks weird, is simple. Okay, so we just said ln means log base e. Right? Didn't we just say that?
Yep.
So, what is log base e of e?
1.
1. Alright, this is huge, guys. This one little thing. That one little thing has tons of application. So anytime you see natural log of e, it simplifies to 1. Because what it's asking you is, what power do I raise e to get e? 1. And we can use that to simplify tons of things. And we're going to start here. Number 2. What can we do with an exponent? It can come out in front. So this is 5 times ln of e. But what did we just define natural log of e to equate to?
1.
1. And 5 times 1 is
5.
5.
4.
So it's just, so wait, so does ln and e just mean, or like, never mind.
Natural log of e is 1. Okay, you try. Number 3.
Oh, you try.
All right, the 2.5 comes out in front.
Yep.
Natural log of e is 1. 2.5 times 1 is
2.5.
2.5. Okay, now this one is 7 ln of e to the 6. This means 7 times ln of e to the 6. What can I do with that 6?
Bring it out in front.
All right, so I get 7 times 6 times ln of e, which is 7 times 6 times 1, or 42.
Wow. Amazing.
All right, you try.
Oh.
Back.
Right, it's
Maybe it's right. Maybe there is no-
It's 4 times 2 ln
You're right.
e. So it's just 8 times.
So when we see ln, the base is e.
Yep, whenever you see ln, you know the base is e.
Okay.
So this becomes 4 times 2 times ln of e, plus 3 times ln of e. So the natural log of e is just 1. So we get 8 plus 9 is
17.
17.
Yeah, boy.
All right.
Alright.
Very cool.
Now, so those were all our evaluate problems. Now we're going to solve. And these are in logarithmic form. So we're going to switch to exponential form to see if we can solve. If it says natural log, what do I always know the base is? E. So it becomes e to the 0 equals x. Well, any number to the 0 power is 1, except 0 to the 0. All right? So that just becomes 1. So even if we take our weird new little number e and raise it to the 0 power, it is also 1. Okay? Number 7, let's switch forms. What is the base? E. What is the exponent? 1. What is the answer part?
E.
X.
X. So E is the answer.
X equals e.
Yep.
So that means x equals 2.71828.
That's right. Approximately 2.71828.
So do we need to write down the number or just?
You just write down E. The only time you would use a decimal approximation if it was a word problem and you were trying to give an answer that made sense.
Oh.
Because you wouldn't say it would be
What do
E
you-
pounds.
Okay.
No, that doesn't make any sense. So then you would convert it to the decimal. All right, number 8. It would become e to the negative second equals x. Now, we don't leave a negative in our exponent, so we would go ahead and do the reciprocal here, guys.
E to the second power over 1.
Yeah, that's right.
Oh, that's the answer?
Yeah, 1 over e squared. All right, let's switch forms on this one. It becomes e to the 1/2 equals x. And what does the 1/2 power mean? Square root. So this is the square root of e.
Could we just leave it as e to the 1/2? Or
No, please. No.
You know what? According to these directions, it wouldn't be wrong. Yeah. It didn't say you can't leave it with negative or fractional exponents. All right, now when we switch forms on this one, we get e to the 3rd equals x minus 2. So we're not done.
E to the third power plus 2.
That's right.
And then we done?
And then we're done.
Oh, okay. That's how we have.
Dewey, you're a
anymore.
genius.
That's it.
I do not like myself.
All right, how are we doing so far?
Why not?
66 of the x.
So far, so good.
Good.
The e as a 10.
Okay. Now, let's go back to some of our favorite things.
Not really.
Condensing and expanding.
Oh no.
Wait.
Okay, so natural logs are logs. So all those properties that we learned with condensing and expanding work just the same here. But instead of writing log, we will write ln. It's natural log. That's really the only difference. So number 11 asked us to condense. What do we get, guys?
3x minus 3x.
ln of 3x. Natural log of 3x. Addition is rewritten as multiplication. So if we condense to a single log.
That makes me so uncomfortable.
Okay. All right. This one, subtraction. What does it become? Division. That's right. Now, this has numbers out in front. So if we're condensing, they have to go back and become exponents.
You don't square the 5, right?
No, just the x.
Just this.
So we get natural log of 5 times the x squared. The subtraction becomes division. Divide by y cubed. All right, now these go the other way. So we're starting with a single logarithm and we're expanding it as much as we can. So the first step would be to break up that multiplication into addition. And then what can we do with the power?
Put it in the front.
We can put it right in front of that natural log. So it's natural log of 3 plus 3 natural log of x. All right, you try. Number 15. All right, the division becomes subtraction, and then those powers can come out in front. Guys, you are more than welcome to do this in that one step and go straight to the answer. I'm good with that. All right, now this one's interesting because when we expand this, we get 5 ln of e minus ln of x. So what happens with that ln of e?
What?
1. So it's just 5 minus ln of x. Okay, so we will never leave an ln of e. We will always simplify it, no matter what the directions say. We always simplify natural log of e. Alright, now this one isn't as cool, but it's got some multiplication up top, some division, a fractional square root, which is a fractional exponent. So let's see what you can do with this one.
I'm taking my private written on Saturday.
Really?
Yeah.
I'm nervous.
It's gonna be so hard. I'm taking my private pilot written test.
So you like studied all that stuff already?
Oh,
Yeah.
I'm doing it now and I hate it.
Yeah, I got a 92 on my first test, and then an 89 on my first test, and a 93 on my second.
Yeah. Can you retake it if you fail?
Yeah, you can take it. I didn't think there's like a limit how many times you can take it.
Alright, did you get ln of 2 plus 3 ln of x minus 1/2 ln of y?
Yay.
Awesome,
So
awesome.
can we like just put the square root in the y? I mean,
The square root would definitely need to change to the exponent when we're expanding.
oh, okay.
Okay? Alright, now we're going to solve. And we follow the same rules if we have logs on one side. We condense. And then switch forms. If we have logs on both sides, we condense if necessary, and then set the answer parts equal to each other and solve. So most of you probably didn't even need to write that because those are our same rules we used for all of our logs. We use them when it's log base e, natural log, same rules. Okay, so we're going to condense over here. So this becomes ln of 3 times x minus 1 equals 2. Now, of course, we could distribute that 3, but we don't have to. Because now we're going to switch forms. And when we switch forms, because it's natural log, it's base e, so it becomes e squared. And you might want to just divide by the 3 right here instead of having to distribute it. So this is what you get. You get e squared divided by 3 plus 1 equals x. Because we have to move this 1 over next. Alright, now if you distributed the 3, you may have ended up with e squared plus 3 over 3.
Yeah.
Is that the same thing?
Yeah.
Yes, it is. So you would have gotten an equivalent answer, which is totally fine. Okay, number 19. We could bring this 2 up, but do you notice that the other side divides by 2?
Yeah.
So I'm going to choose the easiest way, which is to go ahead and divide by that 2. And now I have natural log of x equals 4.
E4.
So e to the 4th equals x. Alright, so number 18 and number 19 both had logs on one side. But number 20 has logs on both sides, which is really the easier kind. So we're going to condense, and so that subtraction turns into division. And because we have logs on both sides, we just set the answer parts equal and solve. So we get x plus 3 equals 5x. Subtract an x. 3 equals 4x. So 3/4. Now, I missed a really important step on these. With logarithms, can the answer part ever be negative? No. And shouldn't we always check?
Yeah.
Yeah,
How to
You don't have
check?
to check these?
you do. And we should have. But if we go back and check all of these,
We don't.
this is positive. So if I plug it in, stays positive. All right, and we know this is greater than 1 because I added 1 to it. It had to be greater than 1. All right, this is positive, so I'm good. And this is positive, so if I plug it in, I've got positive, so I'm good. We always should go back and just kind of glance at our answer and make sure that if we plugged it in, we would still have a logarithm that is defined. So that answer part must be positive. All right, questions? No? Okay, awesome.